Next problem. Let us see. No need thermodynamic properties, because in the thermodynamics we had seen this. Right, compressibility and bulk modulus. Compressibility and bulk modulus we are going to see. Okay. What is meant by compressibility? Compressibility is the reciprocal of bulk modulus of elasticity K, which is defined as the ratio of compressive stress to volumetric strain. Understand? Uh, Consider a cylinder is fitted with a piston as shown in figure. Let V is the value of gas enclosed in the cylinder and P is the pressure of gas when volume is V. Let the pressure is increased to P plus dP due to the compression, and the volume of gas is decreased from V to V minus dV. Understand? So the increase in pressure is equal to final pressure minus original pressure, P plus dP minus P. If we simplify it, PP will get cancelled and dP will be the remainder. So the increase in pressure is dP. Similarly, the decrease in volume is equal to final value minus initial value. V minus dV minus V plus V minus V will be gets cancelled. Okay, gets cancelled, and what is the remainder? dV. Okay, minus dV. A decrease in volume is equal to dV or minus dV. Okay, the volumetric strain is equal to volumetric strain, change in volume to the original volume. Change in volume is minus dV and original volume is V. So volumetric strain is equal to minus dV by V. Minus dV by V. This is the information. And see the next slide. Okay, we are seeing one cylinder, and the cylinder is fitted with gas. Okay, when piston is at outer dead center, cylinder is filled with gas with volume of V, and at that time its pressure is P. Okay, in compression, what will happen? Pressure will increases. Okay, to V plus dV, and volume will be decreased from V to V minus dV. Understand? So we got a increase in pressure and a decrease in volume, and volumetric strain we got minus dV by V. So bulk modulus is the ratio of increase in pressure to the volumetric strain. Increase in pressure is dP. Increase in pressure is dP. Okay. A volumetric strain is minus dV by V. Minus dV by V. So in simplification, we can write dP by dV into V. This is the bulk modulus. Bulk modulus and expression. Compressibility is the reciprocal of bulk modulus. So 1 by K. Likewise, we can write. Otherwise, compressibility is nothing but a ratio of volumetric strain to increase in pressure. Like that also we can express it. Now, come for another slide. Surface tension and capillarity. Surface tension and capillarity. What is meant by surface tension? Surface tension is defined as the tensile force acting on the surface of a liquid in contact with a gas or on the surface between two immiscible liquids, such that the contact surface behaves like a membrane under tension. Okay, surface tension is a as a tensile force which is acting on the surface of a liquid which is contact with a gas or on the surface, okay, between two immiscible liquids, such that the contact surface behaves like a membrane under tension. Surface tension is created due to the unbalanced cohesive forces acting on the liquid molecules at the fluid surface. Okay, surface tension is resulted due to the unbalanced cohesive forces. And molecules in the interior of the fluid mass are surrounded by the molecules that are attracted to each other equally. However, the molecules along the surface are subjected to a net force towards the interior. The apparent physical consequence of this unbalanced force acting on the surface is to create the hypothetical skin or membrane. This membrane will be under the tension. Okay, see this figure, a surface tension. A tensile force may be considered to be acting on the plane of the surface along any line of the surface. See, in liquid, we are seeing one liquid and concentrating on one or two important molecules. One molecule is purely submerged in the liquid and another molecule is floating on the surface. Understand? For the molecule which is submerged in the liquid is having attraction attractional force from all sides. Understand? um, because the molecule is surrounded with so many molecules. So molecule is trying to create the bonds with the other molecules to have the form structure to the liquid. Understand? So this will causes the a certain unbalanced in cohesive forces. Understand? The intensity of molecular attraction per unit length along the any line of the surface is called surface tension. Okay, simple in simple terminology, we can call surface tension as the tensile force acting per unit length. Okay, and this tensile surface tension is represented by the Greek letter sigma. Understand? And it units is Newton per meter. Okay, come for the another slide. Surface tension along the liquid droplet on a bubble. Understand? So this is the one bubble. Okay, droplet, hemispherical droplet. Consider a small spherical droplet of a liquid of radius or capital R. On the entire surface of the droplet, the tensile force due to the surface tension will be acting. Understand? See, 2 pi r. Entire this circumference is 2 pi r. Understand? 2 pi r. Sigma s is the tensile surface tension. Okay, sigma is the surface tension. Okay. Uh, what is the force acting on that surface area is nothing but tensile force. So that tensile force is equal to surface tension into circumferential area. Circumferential area is nothing but pi d. D is the diameter. Diameter is nothing but 2r. Okay, 2 pi r. Circumference of a bubble can be represented as 2 pi r into sigma s. And this tensile force will act on the entire circumference. Understand? This force is acting away from the surface and this pressure force is acting towards the droplet. In this way, the forces must be balanced by two forces. Understand? Consider a small spherical droplet of a liquid of radius r. On the entire surface of the droplet, the tensile force due to surface tension will be acting. Let sigma is the surface tension of the liquid and delta P is the pressure intensity inside the droplet. Okay, R is the radius of droplet. Let the droplet is cut into two holes. The force acting on the half will be equal to will be equal to tensile force due to the surface tension acting around the circumference of the cut portion as shown in the figure. Okay, this is a tensile force and it is acting on entire circumferential length, and it is 2 pi r sigma into 2 pi r. We got it. And the pressure force on the area, okay, pressure is acting on the cross sectional area, pi by 4 d square or simply pi r square. Pressure into area will be the pressure force. These two forces are acting on the droplet. Okay, these two forces will be equal and opposite under equilibrium conditions. For droplet, 2 pi r sigma s is equal to pi r square into delta p. Tensile force is equal to pressure force. Okay, and this pressure force and also see pi gets cancelled. Okay, and r square gets cancelled, and what are the remainder? 2 sigma s. 2 sigma s is equal to r into delta p. Okay, write the expression for delta p. Delta p is equal to 2 sigma s by r by the cross multiplication. Delta p is nothing but the pressure difference. The pressure difference inside and surface and outside surface. So Pi minus P naught is equal to delta P is equal to 2 sigma s by r. This is for droplet. Whereas for bubble, whereas for bubble, it will have two surfaces. Understand? So here we are multiplying with 2. Same. As it is 2, we will get the pressure difference Pi minus P naught is equal to 2 into 2 sigma s. So we are getting 4 sigma s by r. That is the difference between a droplet and bubble. A hollow bubble like a soap bubble in air has two surfaces in contact with air. One is inside and other side. That is the thing. Because hollow bubble, soap bubble will be an air contact in air. So by soap water we can form the water bubble. This water bubble or the soap bubble will fly in air. Understand? Outside surface is in contact with air, and also inside surface is filled with air. So these two surfaces will have the surface tension problem. That is why we have to consider two surfaces. So we are getting pressure difference is equal to 2 into 2 sigma s by r. Okay. These two surfaces are subjected to surface tension, inside surface and outside surface. And come for the one example, problem example. Find the surface tension in a soap bubble of 40 mm diameter when the inside pressure is 2.5 Newton per meter square above atmosphere. Okay, what is given? Diameter of the soap bubble given, initial pressure given, and asking us to calculate the surface tension. D, diameter of the bubble, converted into meters, pressure in excess outside, P is equal to 2.5 Newton per meter square. Okay, for a soap bubble, soap bubble pressure difference P is equal to 8 sigma by D. Okay, 1 minute. For soap bubble, pressure difference Pi minus P naught is equal to 4 sigma by R. 4 sigma by R. Okay, this R can be written as a diameter by 2. Diameter by 2, D by 2. Okay, yes or no? D by 2. So if you simplify it, what will happen? 4 into 2 into sigma s by D will come. Therefore, 8 sigma by D will come. Pressure difference D is equal to 8 sigma by D. In that way, we have to write that expression. If the radius given, directly you can use. If the diameter given, we can substitute that in P is equal to 8 sigma by D. And P value given, diameter given. So from that expression, we can get surface tension as sigma is equal to so and so. If you substitute all the values and simplify it, we will get 0.0125 Newton per meter. And see one more example. The pressure outside of the droplet of water of diameter 0.4 mm is 10 into 10.32 Newton per centimeter square. Atmospheric pressure. Calculate the pressure within the droplet if surface tension is given as. See here diameter given, pressure given, and uh, surface tension given, outside given. So he is asking us to calculate the inside pressure. So what is the given data? Diameter of the droplet given, pressure outside of the droplet 10.2 10.32 Newton per centimeter square. So convert it into Newton per meter square. If we do so, we will get 10.32 to 10 to the power of minus 10 to the power of 4 plus 4. Surface tension given 0.00725 Newton per meter. The pressure inside droplet in excess of outside pressure is given by. Okay. What is this? Droplet. Understand, this is not a bubble. This is a droplet. So P is equal to 2 sigma by D. How this came? Once again, go back to that slide. This is a droplet. Okay, for droplet, pressure difference Pi minus P naught is equal to 2 sigma by R. R is equal to diameter by 2. Diameter by 2. So R can be replaced with D by 2. In next step, 2 will come to the numerator. 2 into 2, 4. Therefore, delta P is equal to 4 sigma by D. Likewise, we have to convert that for a droplet. Pressure inside the droplet is equal to P is equal to 4 sigma by D. If you substitute all these values, we will get pressure is equal to 0.7 Newton 725 Newton per centimeter square. Of course, 7250 Newton per meter square we got. Okay, that value we want to convert it into Newton per meter square. So 1 meter is equal to 10 to the power of 2 centimeter. So as we are making square, we will get 10 to the power of 4 centimeters square. Newton by 10 to the power of 4 centimeters square. So 7 to 50 by 10 to the power of 4. So we will get 0.725 Newton per centimeter square. This is the inside pressure of the droplet. So pressure inside the droplet is equal to pressure P plus pressure outside of the droplet. Outside of the droplet is 10.32 given in the problem. Okay, atmospheric pressure. Okay, the inside pressure is 0.725. Outside pressure 10.32. So what is the total pressure? 11.045 Newton per centimeter square. This is the problem. And capillarity, one of the important property. Capillarity is what is meant by capillarity? Capillarity is defined as phenomena of rise or fall of a liquid surface in a small tube relative to the adjacent general level of liquid when the tube is held vertically in the liquid. The rise of liquid surface is known as capillary rise, while the fall of the liquid surface is known as capillary depression. The attraction or adhesion between the wall of the tube and liquid molecules is so strong enough to overcome the mutual attraction, that is the cohesion of the molecules, and pull them up the wall. Hence the liquid is said to be wet the wet the solid surface. And this capillarity is expressed in terms of centimeter or mm of liquids. Its value depends upon the specific weight of the liquid, diameter of the tube, and surface tension of the liquid. So capillarity depends upon the three parameters: specific weight and liquid, diameter of the tube, and surface tension of the liquid. Expression for capillary rise. Consider a glass tube of small diameter D, dipped at both ends, and it is inserted in the liquids. Okay, say water. Understand, there is a water, and in this water a glass tube is dipped. Okay, let the liquid will rise in the tube above the level of the liquid. Okay, in the tube. Under the state of equilibrium, the weight of the liquid of height h is balanced by the force at the surface of the liquid in the tube. Okay, but the force at the surface of the liquid in the tube is due to surface tension. Very important thing. Under the state of equilibrium, weight of the liquid of height h is balanced by the force at the surface of the liquid in the tube. But the force at the surface of the liquid in the tube is due to surface tension. Okay, you see, once we dip, generally, um, just assume it is a vessel or a beaker, understand, which is filled with water or liquid. Take one glass tube and dip into that glass tube. Dip that glass tube into the water. Because of the capillarity, what will happen? The rises, water will rise into the tube. Okay, and that water level will be higher than the surface level outside of the liquid. So water is filled in the tube to this much height. H is the height of the water level presented in the tube from outside surface. Okay, and if you see, it's a simplification. Let sigma is the surface tension, and theta is the angle of contact between the liquid and the glass tube. Where is this? Say, this is the theta. Okay, water level inclination between glass tube surface and the liquid surface. This much angle theta is taking places. So uh, along its fluid level, surface tension is acting sigma. It is represented with sigma. Height of the liquid in the tube is h. Okay, and weight of the liquid on the height h in the tube is equal to area of the tube, h into rho z. What is the area of the tube? Pi by 4 d square. And see how we got this expression. How we got this expression? What is the expression for W? W is equal to mg. Okay, W is equal to mg. Forget about entire this terminology. This is the mass. This is the mass, and this is the acceleration due to gravity g. W is equal to mg. Okay, and we are exercising mass expression. Area into height is nothing but volume. Area into height is equal to volume. Volume into density is nothing but a mass. In that way, we have to understand. Got it? Mass is nothing but a density into volume. Area into height will be the volume. Understand? So total weight of the liquid is equal to area of the tube into h into density into acceleration due to gravity. So what is the area? Pi by 4 d square. H as usual, density as usual, g as usual. Okay, and vertical component of the surface tensile force. Again, here we are writing the tensile force component. vertical component. Okay, sigma into cos theta. Sigma into cos theta. Okay, sigma into circumference into cos theta. Why here area came? Surface tension is just like a stress. Understand? Surface tension is equal to force by length. Okay. Vertical component of the tensile force is asking. That is why surface tension into circumferential area. Okay, pi d cos theta. Pi d cos theta. Okay, this one, what is the weight of the liquid and vertical component of the tensile force, and these two are balanced by each other. So this weight of the liquid pi y4 d square h rho g is equal to sigma pi d cos theta. Okay, once we simplify this expression for h, we will get 4 sigma cos theta by rho gd. Okay, what is the expression for capillary rise? Why we are calling it as a capillary rise? In a glass tube, water level rises from the surface at a height of h. That is why we are calling it as a capillary rise. Okay, what is that expression? H is called 4 sigma cos theta by rho z d. And the cap again here expression for capillary rise. The value of theta between water and clean glass tube is approximately equal to 0. Understand? And hence the cos theta will be equal to unity because cos 0 is 1. Then the rise of the water is given by H is equal to 4 sigma rho ZD. And also this contact angle depends on both the liquid and the solid. Liquid and solid. And if theta is less than 90 degrees, the liquid is said to be wet. Said to be wet the solid. However, if theta is greater than 90 degrees, the liquid is repelled by the solid and tries not to wet it. For example, water wet the glass but not wax. Okay, mercury on the water other hand does not wet the glass. So what is the expression for capillary rise? H is equal to 4 sigma by rho ZD. Right, lastly, only one topic. Capillary expression for capillary fall or depression. Here we are comparing these two phenomena with the two fluids. We are taking water. We are taking water in a beaker and mercury in another beaker. Okay. Because of its nature, what is happening? Water is wetting the surface. Understand? Water is wetting the surface, and this that wetting angle is phi. You just assume or theta. Okay, mercury is there. Mercury is not wetting the surface, so its level is falling downwards, and its angle is phi. Okay, and in these two beakers, we are dipping two glass tubes. So water is rises up into the glass tube, whereas in mercury, water level is falling inside the glass tube. See, in the tube in which we dip the water, we are getting concave surface, which is meniscus. Understand? Okay. In the mercury tube, we are getting convex surface because of the nature of two substances. Water has adhesive forces very much higher than cohesive forces. But whereas mercury, cohesive forces are very much higher than adhesive forces. That is the main reason. Okay, expression for capillary fall. If the glass tube is dipped in mercury, the level of mercury in the tube will be lower than the general level of the outside liquid as shown in the above. Okay, expression for capillary fall. Okay, let H is the height of depression. See, from surface to decreased level is represented by the term H, and the theta is the angle between the falling level and the glass tube surface. Okay, then equilibrium, let H is the height of depression in the tube. Then in equilibrium, two forces are acting on the mercury inside the tube. First one is due to surface tension acting in the downward direction and is equal to sigma pi d cos theta. Sigma pi d cos theta. Second, the force is due to hydrostatic force acting upward and is equal to the intensity of the pressure at a depth of h into area. See, this is the two forces. Pressure force, it is acting, P is equal to pi by 4 a square, and hydrostatic force, rho c h, pi by 4 d square. P is equal to rho c h, we know it. So P into pi by 4 d square. P is equal to rho g h into pi by 4 d square. Right. These force due to surface tension and force due to pressure head will be balanced by each other. Understand? So from this we can write expression for capillary fall or capillary depression 4 sigma cos theta by rho z. If you observe, we got same expressions. Understand? For capillary rise also we got 4 sigma by rho z, 4 sigma cos theta by rho z. For capillary rise fall also we got the same expression 4 sigma cos theta by rho z. Okay. For capillary rise, the rho is the density of water, and for capillary depression, rho is the density of the mercury. And for capillary rise, theta is approximately equal to 0. And for capillary fall or depression, theta is equal to 128 degrees. Very important one. This is okay. Um, Okay, boys, so let us see one more problem for capillary rise and capillary fall. Within 5 minutes, I am going to conclude the session. Okay, just read the problem. Calculate the capillary rise in a glass tube of 2.5 mm diameter when immersed vertically in a water and mercury. Take surface tension sigma for water and sigma for mercury in contact with the air. The specific gravity of mercury is 13.6 and the angle of contact is 138 degrees. So here, what's the problem? There are two beakers are there, two glass tubes given. One a glass tube is dipping into water and as well as mercury. And he is asking us to calculate the capillary rise in glass tube. Okay. So here, what is the data given in the problem? Diameter of the tube, 2.5 mm, converted into meters, surface tension for sigma and surface tension for mercury, specific gravity of mercury given in the problem. Okay. Density is equal to specific gravity into 1000. We got it. First one, capillary rise for water. So for water, theta is equal to 0. H is equal to 4 sigma by rho z. If we substitute all these things, we will get 0.0118 meter or 1.18 centimeter. For mercury, What is the capillary rise? Angle of contact between mercury and glass tube is 130 degrees. E given. H is equal to 4 sigma cos theta by rho ZD. 4 into 0.52 into cos 130. Density of mercury is equal to 13.6 into 1000. And the G value as usual and the D value as usual. Okay. So now here we are getting minus value. We are getting minus value because how this minus value came? Cos angle, because of the cos angle. Cos 130. Cos magnitude value in the second quadrant is negative. That is why we are getting minus value. So indirectly, what is getting? This is indication of capillary fall or capillary depression. That is the thing. The negative sign indicates the capillary depression. Okay, last problem for this session. Find out the minimum size of the glass tube that can be used to measure water level if the capillary rise in the tube is to be restricted to 2 mm. Consider surface tension of water in contact with air as 0.73575 Newton per meter. What is the thing? Uh, minimum size of the glass tube. We have to find out. Water is using and the capillary rise is restricted to 2 meter. Consider the surface tension given in the problem. Okay, indirectly capillary rise H value given, surface tension sigma given, diameter of the tube we have to find out, and angle of the contact of water. For capillary rise, theta is equal to 0, and density of water, rho value we know. For water, that too for capillary rise, H is equal to 4 sigma by rho ZD. So substitute all the values. H value we know, sigma value we know, rho value we know, G value we know. So from this we can calculate the diameter of the tube. It is approximately we are getting 0.015 meter. So it means 1.5 centimeter. So this is the minimum diameter of the tube should be 1.5 centimeter. Okay, boys. Remaining things we will discuss on Monday. Okay, we will meet you on Monday. Thank you, and now you can leave. Okay, one thing I am saying: try to get the textbooks or any other spectrum or any material from your seniors or friends. Okay, and follow the class simultaneously. Okay, right. Bye. Leave. You can leave now. Manikumar.
Sir,
Okay, are you following?
following sir.
Right. నేను టెక్స్ట్ బుక్స్ ఉంటే కూడా చదువుకోండి. వినయ్ కుమార్,
Yes, sir.
విష్ణు తేజ అండ్ షేక్ ఇమ్రాన్, ఉప్పాల హరీష్, ఆల్ go through
Yes,
the
sir.
textbooks also. Okay, right.
Yes.
Thank you. Thank you.